What if everything the car industry told you about the limits of electric vehicles was based on a design flaw that nobody bothered to fix for 20 years? Not a chemistry problem, not a physics problem, not an unsolvable engineering challenge requiring a breakthrough that hasn't happened yet. A design flaw, a decision made in the early days of modern electric vehicles that got locked in, copied, passed down from one generation of cars to the next, and accepted as simply the way things had to be. BYD fixed it. And the moment they did, every objection you have ever heard about electric cars, the charging time, the range anxiety, the winter performance, the weight penalty, collapsed simultaneously. Not one at a time, not gradually over the next decade as incremental improvements compound. All at once, in a single architecture that went into production vehicles that you can walk into a showroom and buy today. The number they put on a screen in March 2025 to demonstrate what fixing that flaw made possible stopped a room full of automotive engineers mid-breath. 5 minutes, not 5 minutes to add a bit of range to extend a journey. 5 minutes to go from nearly empty to 250 miles of real driving range. 5 minutes that is shorter than most people spend deciding what to order at a drive-thru. 5 minutes that makes the last remaining practical argument against switching to electric, the one about standing at a charging station while the car next to you fills with petrol and drives away, simply disappear. But the 5 minutes is not even the most interesting part of the story. The most interesting part is what had to be true about the car itself before 5 minutes became possible. And to understand that, you have to go back 30 years to a rented room in Shenzhen and a chemist who spotted something the rest of the world had missed. Before we go any further, hit the like button right now. These videos take significant research and production to put together properly, and every like directly helps this channel keep making them. Subscribe and turn on the notification bell so you are there when the next one lands. All right, here we go. In 1995, Wang Chuanfu was 29 years old with a chemistry degree, approximately $300,000 in starting capital, and an observation that was simple enough to fit in a single sentence. Japanese manufacturers controlled the global rechargeable battery market. They set the prices. Nobody was seriously challenging them. And the reason nobody was seriously challenging them was not because the technology was impossibly complex. It was because nobody had invested the time and resources to understand the chemistry deeply enough to produce it more efficiently. Wang decided to be the person who invested that time. His approach was methodical and unglamorous: acquire existing battery products, take them apart, map every component, every material, every step in the manufacturing process. Understand not just what the product was, but why every decision in its construction had been made, and whether each of those decisions was actually optimal or simply inherited from whoever had done it first. What he found consistently was that there was room to produce more efficiently, room to reduce cost without reducing quality. Room that existed because established manufacturers had never needed to look for it. Within 5 years, BYD was the largest nickel-cadmium battery manufacturer on Earth. 2 years later, they held the top position in lithium-ion supply. Nokia and Motorola were clients. The company that had started in a single rented space was now supplying the energy storage infrastructure of the global mobile phone industry. But the decade of battery manufacturing had produced something more valuable than revenue and market share. It had produced an understanding of energy storage that went deeper than any car company in the world possessed. Because car companies thought about batteries the way they thought about tires or windscreens, as components with specifications, things you sourced from people who made them and then engineered your product around. Wang's team did not think about batteries that way. They thought about batteries the way a surgeon thinks about anatomy, from the inside out, at the level of chemical reactions and material properties and failure mechanisms and efficiency losses that occur in the spaces between the components that appear on a specification sheet. That difference in how they understood the thing is the entire reason what happened next was possible. When BYD entered the automotive business in the early 2000s, the strategic logic was clear to Wang, even if it was opaque to almost everyone watching from outside. The internal combustion engine was a transitional technology. The electric vehicle era was coming. And an electric vehicle is, at its most fundamental level, a battery system with a chassis and a motor attached to it. Control the battery, control the car. For the first decade, BYD made vehicles that were competent rather than remarkable. The products were not the point yet. The point was building the manufacturing infrastructure, the engineering talent, the patent portfolio, and the platform that would eventually carry something genuinely different. In 2020, BYD made a decision that puzzled most of the automotive industry. While competitors were moving toward battery chemistries that offered higher energy density, BYD committed their future to lithium iron phosphate, a chemistry that most of the market had already concluded was a dead end. The reasoning was simple and widely agreed upon. Lithium iron phosphate stored less energy per kilogram than the alternatives. In a market where range was the number one consumer concern, less energy density meant less range, and less range meant fewer buyers. BYD reached a different conclusion from the same data. Lithium iron phosphate had properties that the higher density chemistries did not. It was thermally stable, meaning it did not want to catch fire when stressed, punctured, or overcharged the way other chemistries did. It lasted significantly longer through charge and discharge cycles, meaning the battery degraded more slowly over years of use. It did not depend on cobalt, a material whose extraction is both expensive and ethically fraught, and it was cheaper to produce at scale. The energy density gap was real, but BYD believed it was an architectural problem wearing the disguise of a chemistry problem. The cells were not getting full credit for the energy they could store because too much of the space around them was being wasted on packaging and protection. Fix the architecture and the chemistry becomes competitive, maybe more than competitive. They redesigned the cell geometry from first principles. Conventional battery cells are cylindrical or roughly rectangular, built to be stacked into modules, modules built to be assembled into packs. Each transition from cell to module to pack consumes space and adds mass without storing a single additional joule of energy. The module layer exists primarily to make the cells easier to handle and replace. It is a manufacturing and maintenance convenience that the end user pays for in weight and volume. BYD eliminated it. They created cells that were long and flat, spanning the full dimension of the battery pack, slotting directly into the structural frame without any intermediate module housing. No module layer means no module packaging. No module packaging means more of the available space is occupied by cells rather than by the infrastructure surrounding cells. The result was a pack where approximately 76% of the total volume was active energy storage material rather than the structural and protective elements surrounding it. They called it the blade battery. To demonstrate the safety properties publicly, they drove a fully loaded 46-ton truck directly over a fully charged pack. The pack did not rupture. It did not ignite. It barely deformed. Wang Chuanfu said his personal ambition was to remove the phrase spontaneous combustion from the electric vehicle vocabulary entirely. That statement carries a specific kind of weight when it comes from the person who designed the battery rather than the person who wrote the press release. The blade battery was a genuine step, but it was still a box, better engineered, more space efficient, demonstrably safer, but fundamentally still a separate unit that sat underneath the car and did one job. What came next was not an improvement to the box. It was the elimination of the box as a concept. Here's the design flaw that nobody fixed for 20 years. Every electric vehicle built during the modern era of the technology was designed around a separation between the energy storage system and the structural system of the vehicle. The battery pack was a component. The car was built around it. The battery did its job and the body structure did its job, and the two systems coexisted without meaningfully contributing to each other. This separation had consequences that compounded against each other in ways the industry managed rather than solved. The battery pack added mass to the vehicle without contributing to its structural rigidity. A heavier vehicle requires more energy to accelerate, decelerate, and maintain speed. More energy required means a larger battery needed to achieve the target range. A larger battery means more mass. More mass means more energy required. The cycle is self-reinforcing, and every EV manufacturer in the world is somewhere inside it, trying to exit by improving efficiency at the margins, rather than questioning the architecture that created the loop. The packaging surrounding the cells consumed a significant proportion of the total space available for energy storage. Protective casings, cooling channels, wiring management, structural frames to hold the modules, all of it necessary given how the system was designed, all of it occupying volume that could theoretically store energy but did not. The cells themselves were a fraction of the total package. Cold temperatures attacked the chemistry directly. The electrochemical reactions inside the cells slowed at low temperatures. Accessible capacity dropped. Charging rate dropped because cold cells could not absorb current at the rate the infrastructure was capable of delivering. The car consumed energy maintaining the battery within a functional temperature range. The owner experienced shorter range, slower charging, and a general degradation of the product's capability precisely in the conditions where reliable performance mattered most. And charging time remained structurally limited by the architecture regardless of how powerful the charging infrastructure became. You can build a charger capable of delivering enormous amounts of power. If the thermal management of the battery cannot handle the heat generated by accepting that power quickly, the charging rate has to be limited to protect the cells. The bottleneck was not the charger, it was the battery design. BYD looked at the complete picture of these interconnected limitations and concluded that solving any one of them in isolation would not move the needle far enough. They were all symptoms of the same cause. Separate the structure from the energy storage, and you create a system that is perpetually working against itself. The question they asked was the one that sounds obvious in retrospect and radical at the time. What if the battery and the car were the same physical thing, not connected, not integrated in the sense of being placed close together and wired efficiently? The same thing. The cells themselves forming part of the load-bearing structure of the vehicle. The floor you sit on, the frame that connects the front and rear of the body, the element that distributes forces during cornering and absorbs energy during impact. Cell-to-body integration is the engineering answer to that question. In this architecture, the top surface of the blade cell array becomes the actual passenger floor. The cells span between structural nodes of the vehicle body, transferring load the way steel crossmembers transfer load. The battery is not underneath the structure. The battery is part of what the structure is made of. The analogy that makes this tangible is the difference between a building that has a heavy piece of machinery sitting on its floor and a building where the machinery is part of the floor. In the first case, the machinery adds load that the structure has to accommodate. In the second case, the machinery is load-bearing. It contributes to the structure rather than burdening it. The measurable outcomes of this change are significant enough to deserve specific numbers. Structural testing found that cell-to-body construction produced a vehicle body approximately 70% more rigid than the previous architecture. That level of torsional stiffness puts the car in the same category as vehicles at significantly higher price points that achieve similar rigidity through exotic materials, advanced manufacturing processes, and engineering investment measured in decades. BYD reached the same destination by changing where the battery lives rather than what the body is made of. The efficiency improvement comes from what gets removed when you eliminate the module layer and reduce the structural packaging around the cells. With approximately 76% of the system volume now occupied by active cells, the same physical footprint stores dramatically more energy than a conventional pack design using the same chemistry. This is where the 600-mile range figures come from. Not a bigger battery, not a more energy-dense chemistry. The same chemistry, in the same space, doing its job properly, because the architecture finally lets it. The weight reduction compounds the benefit. Less packaging means less mass for the same energy storage. Less mass means the car needs less energy to move itself. Less energy required for movement means more energy available for range. The cycle that was working against every EV designer for 20 years starts working in the other direction. Then comes the charging. When your battery is integrated into the structure of the car rather than sitting inside a protective box, the thermal management changes fundamentally. The thermal mass of the vehicle structure itself becomes part of the temperature management system. Heat generated during rapid charging distributes across a larger physical system rather than concentrating in a contained unit. This is what makes extreme charging rates achievable without damaging the cells. In March 2025, BYD demonstrated a charging system delivering 1,500 kilowatts of power to a vehicle built on this platform. To give that number context, a fast public charger today typically delivers between 50 and 350 kilowatts, depending on the location and the vehicle. BYD's system delivers more than 4 times the upper end of that range. At 1,500 kilowatts, the result is 10% to 70% charge in 5 minutes. In their flagship sedan, that 5-minute window adds approximately 400 kilometers of driving range, around 250 miles. Stay with that for a moment. Because the implication is not just that charging is faster. The implication is that the charging stop is no longer meaningfully different from a petrol station stop. The primary behavioral objection to electric vehicle ownership, the one that persisted through every improvement in range and every expansion of charging networks, was the time cost of the stop itself. 5 minutes does not just reduce that objection. It removes the premise of it. The cold weather performance deserves its own moment because it represents a genuine and persistent failure of current electric vehicle technology that affects millions of owners and has shaped the perception of the entire category in cold. Climate markets at minus 30 degrees Celsius, a temperature that represents genuine extreme winter conditions beyond what most drivers ever face. BYD system charging from 20% to 97% takes approximately 3 minutes longer than it takes at room temperature. 3 minutes, not doubled. Not slowed to a crawl while the battery management system warms the cells before accepting charge. 3 minutes more than optimal. This is possible because the thermal management built into the cell-to-body architecture maintains the cells within their functional operating range, even under extreme ambient temperatures. The structure that the cells are part of has thermal mass that buffers against external temperature swings. The cells do not get cold the way cells in an isolated box get cold, because they are not in an isolated box. They are part of a larger thermal system that changes temperature more slowly and more evenly. For anyone who has sat at a charging station in January watching the rate climb at half the speed the app predicted, watching the estimated completion time stretch as the temperature dropped outside, this is not a minor improvement. It is a different category of winter experience. The vehicle that carries this technology in its most fully realized form is the Yangwang U7, BYD's flagship full-size luxury sedan. Under Chinese certification standards, it achieves a range figure above 1,000 kilometers on a single charge. Real-world driving produces lower numbers because it always does. But even adjusted conservatively for real conditions on real roads and real weather, the range sits in territory where the question of whether you will need to charge during a given journey becomes irrelevant for the vast majority of journeys most people actually take. Here is the part that separates a technology announcement from a technology deployment. A 5-minute charging system is only meaningful if there are places to use it. BYD understood that delivering a vehicle capable of this performance without the infrastructure to support it would produce exactly the kind of early adopter frustration that damages category perception rather than building it. They solved the infrastructure problem before the car reached customers. The engineering challenge with 1,500 kilowatt charging is that drawing that level of power instantaneously from the electrical grid at thousands of simultaneous locations creates demand spikes that the grid infrastructure cannot handle. Every watt the charger delivers to a car has to come from somewhere immediately upstream, and the grid was not designed for that kind of instantaneous peak demand. BYD's answer is built into each charging station. Every flash charging station incorporates its own energy storage system. Throughout the day, the station draws power from the grid at a slow, steady rate that the local infrastructure handles without difficulty. That energy accumulates inside the station. When a car pulls in, the station releases its stored energy at full speed directly into the vehicle without placing any sudden demand on the grid at all. The station spends the whole day filling up so that it can empty itself in 5 minutes when a car arrives. The grid never sees the spike, the driver never sees the wait. BYD had more than 4,000 of these stations operational before the first car using this technology was delivered to a customer. Their target for 2026 is 20,000 stations across China. To put that in context, the entire United States currently has approximately 6,500 Tesla supercharger stalls in total. BYD is aiming to deploy 3 times that number of stations capable of charging at 4 times the speed in a single country in a single year. The network is not a future commitment. It is current infrastructure that was being built while the car was still being engineered. This matters enormously because the historical failure pattern for new charging technology follows a specific arc. The technology arrives, early adopters buy the vehicles. The charging network is sparse because operators will not invest in infrastructure for a small user base. Users have a frustrating experience that shapes perception of the technology for years. BYD broke that pattern by building both the vehicle and the network simultaneously and ensuring the network preceded the vehicle. The scale at which BYD operates as a company gives this technology a momentum that individual announcements cannot fully convey. Last year, BYD sold over 4 million vehicles across a lineup that spans from entry-level city cars to high-performance luxury products. Cell-to-body integration is not a feature confined to one flagship model justifying a premium price. It is a platform, and platforms propagate across product lines as manufacturing processes mature and per-unit costs fall. Every major technology that began in premium vehicles has followed the same path downward through the market as volume scales and costs reduce. The structural battery platform that currently exists in a flagship sedan will appear in mainstream family cars, then in entry-level products, then in commercial vehicles and fleet applications where the economics of reduced charging time and improved range have immediate and measurable financial implications. The same physics that makes cell-to-body integration advantageous in a luxury sedan makes it advantageous in a delivery van or a long-haul truck. The application scales. The insight does not change. Every competitor currently building electric vehicles is looking at what BYD demonstrated in 2025 and doing an honest internal assessment of the gap. Some have structural battery development programs underway. Several have made announcements about future cell-to-body architectures. None has yet combined cell-to-body construction, 5-minute charging, cold weather performance at this level, and a deployed charging network in a single production vehicle available for purchase today. The benchmark moved. It moved in one event, in one announcement, with one number on a screen. So let us bring this back to the decision that actually matters. The one you or someone you know will make in the next year or two when it is time to replace a car. The three objections that have accounted for the majority of hesitation around electric vehicles for the past decade were always the same three things. Charging takes too long. 5 minutes at 1,500 kilowatts makes that statement past tense. The range is not enough. 600 miles in production models and over 1,000 miles in the flagship makes that statement past tense. Winter destroys the performance. 3 extra minutes at minus 30 degrees makes that statement past tense. When all three disappear simultaneously, the decision stops being a trade-off calculation. A trade-off calculation is what you do when you are choosing between options that each have meaningful advantages and meaningful disadvantages. When the disadvantages of one option are removed, you are no longer making a trade-off. You are making an obvious choice. The structural benefits extend the value beyond just the battery performance numbers. A body that is 70% more rigid than its predecessor handles with greater precision and communicates the road more honestly through the steering. Forces during cornering distribute across a larger, stiffer structure rather than concentrating in flexible points. In the event of an impact, energy distributes across the vehicle structure more effectively because the battery is part of the structure rather than a vulnerable component underneath it. The long-term cost trajectory points in one direction. Fewer separate systems, less packaging material performing no energy storage function, more of the physical system dedicated to its primary purpose. As cell-to-body manufacturing matures, the cost per vehicle decreases. The technology that currently justifies a flagship price point has a clear and well-traveled path into vehicles at mainstream price points. There is something worth sitting with in the origin of all of this. The company that just redefined what an electric car can do did not come from the automotive industry. It came from a rented room in Shenzhen where a 29-year-old chemist decided to understand batteries at a level the established players had never needed to bother with. The 30 years between that room and a 5-minute charging demonstration in 2025 were not 30 years of trying to build a better car. They were 30 years of building a deeper understanding of energy storage than anyone in the car business possessed. When you understand something at that level, you eventually see the design flaws that everyone else has been managing as if they were natural laws. The battery does not have to be a box underneath the car. That was never a law. It was a habit. And habits, unlike laws, can be changed. BYD changed it. And the car industry will spend the next decade catching up. If this video gave you something to think about, hit the like button before you leave. It costs you 1 second and it makes a genuine difference to this channel. Subscribe and turn on notifications so you are there when the next one drops. Leave a comment with your honest answer. If there was a 5-minute flash charger near your home right now, does that finally make the switch feel like the obvious decision? I read everything you write. See you in the next one.